So waves are a motion of a disturbance, and we talked about this in our waves section. And the source of all wave motion is a vibration. So we're disturbing a medium. Um, at least up in this point, we've looked at things disturbing a medium like air or water or a slinky or a string, a lot of different things that material things. So, we've looked at a lot of different kinds of waves. We looked at sound waves. We've looked at a variety of mechanical waves. We've looked at ocean waves. A lot of things with waves. It's important to distinguish the two different kinds of waves categories of waves. We looked at longitudinal and we looked at transverse, but in the past, this is another category that we need to concentrate on as well. Spherical versus cylindrical wave fronts. If you look at the one on the left, this might, help you recall something like maybe like a wave in the ocean or the beaker. You dip your finger in the water in the beaker, you see the wave go out cylindrically like that. And we've also looked at waves that are point sources. For instance, sound coming out of a speaker as a point source. If I'm talking and I'm not facing you, you can still hear me because my sound is going out spherically. And so, it's important to distinguish between these two, and understand, what's happening with each. With a point source, we know that sound goes out spherically, and we also know that light goes out spherically. And so, 4 pi r squared is the surface area of a sphere. So, if you double the distance away from either of these sources, it's going to be 1/4 as strong because it's a matter of r squared. It's an inverse squared relationship as it spreads out. In this clip, if you want to copy the URL, you can see the motion of the water going through a tank that they make for testing. And you'll see those wavefronts go through there. Wavefronts and waves are important to distinguish. If you're looking at a two-dimensional wave, if you look at the picture in the top here, and the wave is going from left to right in this case, right? The crests are right here, the troughs are right here, and the wave fronts are perpendicular to the motion of the wave in this case, right? So if you look at these magenta or pink planes, they're going right through the crests, and with the caption here, surfaces through crests and normal to the direction of energy propagation of the wave are called wave fronts. Rays are mathematical lines perpendicular to the wave fronts and give the direction of energy transfer. And so, look at the definition here. A wavefront is the surface through crest and normal to the direction of the energy of the transfer of the wave. Lines in the direction of the energy transfer of the wave, and hence normal to the wavefronts are called rays. And so we can see the ray here, going from left to right. And then we can see, the wavefronts. Each of these, a full wavelength away here from a wavefront to a wavefront. Okay, so if we consider a light bulb, and let's say this is a 100-watt light bulb, what this means is every second, 200 joules of energy is emitted. And that's what a watt is, right? It's a joule per second, how many joules per second. And so if we look at let's say this light is going out spherically, as the light spreads out, the intensity gets less and less and less as it gets further out. And it spreads out spherically according to this equation, right? The power of the source gets spread out by the surface area of the sphere because this is going out, as a sphere in all dimensions or all directions. And so, we get in a certain intensity. So let's say that we have a 400-watt light bulb. We're 3 meters away from it. Go ahead and calculate the intensity at that particular spot. In fact, this would be the same as the intensity if you were 3 meters away, somewhere around here or somewhere around here, right? Anywhere along that sphere around. So go ahead and calculate that and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so we take our power divided by the surface area of the sphere. The intensity of that light will be 3.537 watts per meter. Another unit for intensity in terms of light intensity is lux. When we looked at sound, we just left it as a watt per meter squared in terms of intensity, but there is actually a special unit for it, and it is lux for intensity of light. All right, so let's say that the average power of the sun is 4.7 times 10 to the 25th watts, and we're an average distance of 149.6 million kilometers away. On 1 square meter of Earth, assuming no atmosphere, what would the intensity of the light be coming from the sun? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we take that power. We're going to need to figure out how many meters away we are, and we should get 167.119 watts per meter squared on 1 square meter of Earth. So in other words, on 1 square meter of Earth, in every second, we get 167.119 joules. That's what that would mean. So if you look on your data booklet under section 4.3, you'll see a section for wave characteristics. And we're going to focus here on these two right now. We're going to focus on this one later when we're talking about light and more specifically polarization. But let's take a look at these first two. Here's some cylindrical wave fronts, in this clip here, that if you want to take a look at that. Let's go ahead in this one and compare the amplitude of a 0.5 meter amplitude wave compared to a 1.5 meter amplitude wave. So we'll compare the two. So if we look at this, right, the 1.5 meter wave and a 0.5 meter amplitude wave, we know that the intensity of the wave is directly proportional to the amplitude squared. And that's what we're going to focus on here. So, how much more intensity does this wave have than this wave? If you've ever been to the beach, and especially if it's, there's a storm out in the Atlantic, the waves can get pretty huge, and the intensity of those waves really increase with amplitude. And so if we look at this relationship, right, it's a squared relationship. So we have 0.5 squared, 1.5 squared, 0.25 versus 2.25. And so if we compare these two, it's actually 9 times as intense. If you look at the amplitude, this is 3 times the amplitude. And because it's 3 times the amplitude, that is, squared, and so it's going to be 9 times the intensity. All right, so let's say we have this sailboat, and we have a amplitude of 27 meters for this wave and 13 meters for this wave. So pretty extreme at any rate. So how do the amplitudes, or how does the intensity compare? So I'm going to let you try this one. Go ahead and pause the clip and use the relationship there with intensity to figure out what's going on. So go ahead and pause the clip and do that, and then when you're ready to check, you can hit play to continue. Okay, so we've got 27 squared, 13 squared is the amplitude, and we get the ratio 729 to 169. It'd be 4.3 times greater, and so the intensity of that wave versus the other one would be 4.3 times greater intensity. So what kind of waves require a medium? And so the waves that we've looked at, they're mechanical waves. And so we've looked at a lot of different kinds of mechanical waves, and they can fall under the categories of transverse and longitudinal. And it's important to remember the distinction between those. If you remember, with a transverse wave, the movement of the particles are perpendicular to the wave motion. So the direction of the energy is from left to right, but then the particles are moving up and down in this case. This is in contrast to a longitudinal wave. Let's say the the energy is going from left to right, and then the particle moves back and forth, so it's parallel. The particle movement is parallel to the wave motion. It's also important to remember with reflection with a wave. And so if a wave hits a fixed end, the wave is inverted and it's 180 degrees out of phase. If it's open end, the energy of that wave can travel up and then down and send it back. And so the energy of that wave is, in the reflection, it keeps the same phase, so 0 degrees. So what I want us to do is derive the equation for a string standing wave for the first, second, and third harmonics. This is something that you need to be able to do, and this is good review from our unit of sound. And so what I want you to do is go ahead and pause the clip. Go ahead and draw out, this is the first harmonic, but you can draw the second and third, and then see if you can derive the equation for stringed instrument. It turns out on your equation sheet, you're not given that. You're expected to be able to derive this. And so go ahead and pause the clip and give that a try. And when you're ready to check, you can hit play to continue. All right, so the rest of that wave, right, we could draw there. And we have the L is the length of the wave. And 2 times L in this case would be equal to the wavelength, right? And so V equals frequency times wavelength, the frequency times 2L in this case. And so for solving for frequency, it would be V over 2L. If we look at the second harmonic, looks like this. And the length is equal to the wavelength in this one. And so wavelength is equal to L. Frequency is V, the speed of the wave, divided by L. We've got that. And then for this one, we would need 2/3 of the length, right? Just to this point. So 2/3 of this to be able to get the wavelength. And therefore, if we place that in there, it'll look like this. So, frequency is 3V over 2L. So it turns out, right, in each spot, with the original one being 1, the second one being 2, the third one being 3, that's going to be the harmonic number. And so that's the derivation for the string standing wave. Now we're going to derive the equation for an open standing wave, open type situation, instrument or sound cavity. So go ahead and see if you can remember how to draw the harmonics, first, second, and third harmonics for open. And then just like we did with the string, see if you can derive the equation for the open string system. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we've got the and this could be a variety. We've got a compression here and then a rarefaction here. You could have had a rarefaction here and then a compression over here, either way. And if we were to draw the wave on top of it, it's coming from here down to here. And then the rest of the wave would look like this and then like this. Or if you drew it like this, you're down here up to here. The rest of the wave would be here and then it would go off here. And so if L is the length of the pipe, 2 times L would be equal to the wavelength, and V equals frequency times wavelength, so you can place that in there. And we have V equals frequency times 2L. For the second harmonic, we've got our length here. We have you've got the compression, then trough, rarefaction, and then back to a compression. And so in this case, and I didn't draw it out here, I can do that real quick. So like this, so crest to a crest. V equals frequency times wavelength, and L is equal to the wavelength, and so we've got that. And then the final one would be the situation here. You've got the compression node, rarefaction node, compression node, rarefaction. And so in this case, it would be 2/3 L, and we've got that there. And so it would be 3/2 V over L. So therefore, just like we had before, the integer n needs to be here, representing the harmonic number. And we have our equation. All right, so for closed end, I want you to derive the equation for the closed-end instrument. Remember, with open closed, only odd harmonics are going to be present. So you're going to have the first, fifth, or first, third, and fifth harmonics that you can do. So go ahead and try your best with that. Pause the clip and give your best shot with that. And when you're ready to check, you can hit play to continue. Okay. So we know we're going to have a node at the closed end. It's always that way. So the first possible harmonic will be like this. We'll have the node and then the antinode. And then, you know, how much of a full wavelength is this, right? So this is 1/4 of it. So 4 times L will be equal to the wavelength. And we've got that there. Now, with the higher harmonics, you know, we've got the this would be the next step would be a node, has to be a node, and then come to a compression, and then node, and then rarefaction. So in this for this one, it would go compression, or I mean node to a compression, node to a rarefaction. And so we would, and then the rest of the wave would be like this, right? So it's 3/4 of the way there. It's not all the way there. So we would need 4/3 of L to be equal to the wavelength. And with that 4/3, we see that 4 here, right? So that's there. And then the 3 represents the harmonic number. So then this is actually the third harmonic, right? And then we have, you know, the fifth is adding another node and an antinode. All right, so let's say that we had a closed box, and what kind of wave would form inside there? Now, if you know about open ends and closed ends, we know with closed ends we must have nodes. So I'm going to let you try this one. See if you can derive the equation for a situation with a closed situation with resonance inside with air, and we'll see how you do. So go ahead and pause the clip and try this, and when you're ready to check, you can hit play to continue. All right, so node to compression and then back to a node, and this could have been node to a refraction and then to a node. So if you think about it, if you're going from here to a compression and back to a node, you'd have to go down here and then back to here. So this is going to be L 2 times L. So this turns out to be just like a stringed instrument or open instrument. But the fact that we have nodes here, right? So nodes to a compression, node to a rarefaction, back to a node. In this case, you know, L is the length, and we've got L in there for that. So, you know, same string as a stringed or an open instrument. Oh, no. So what is V in this one though, right? So if you think about what's actually resonating, it's the air inside the tube is resonating, right? And so that air is shaking inside, and that's what we've got there. All right, so let's say we have a situation here with a sound source played at an open end, and the other is closed, and let's say a frequency of 21 hertz is played, and let's say we sprinkle some powder inside the tube, and we notice that the power collects in heaps 8 centimeters apart. And we want to figure out the speed of sound this way. And so let's go ahead and draw the pipe. One end's open, the other end's closed. And let's say that the powder is collecting, you know, in certain spots where the air is still. And so the air is still at the nodes, and it's excited at the antinodes. So yeah, why don't you go ahead and try from here, see if you can figure out the speed of sound based on this information here, and then when you're ready to check, you can hit play to continue. Okay, so it's going to push the powder at the nodes, and therefore, you know, a node to a node, no matter what kind of wave that you got, is half of a wavelength. So if that's 8 centimeters apart, and you know, we've got our uh, twice that, right? That's going to be the 16 centimeters would be a full wavelength. Therefore, it's 0.16 meters. We have the frequency, and so the speed of sound in this tube is 336, which is, you know, pretty typical for normal air.